Okay, so differentiation. There we go. Okay, so in this section, I'm just going to list a couple of rules that we were pretty much already familiar with. Now, just as I said, we're going to add a little vector twist to it. So the first one is just the constant multiple rule. I'll name it here. So constant multiple, there we go, and rule. Okay, so what this is saying is basically for any constant c, and constant again is just a number, then this is true. C times r of t prime. So if you multiply r of t times a constant, like 2 or 3 or whatever, and then you take the first derivative, this is going to be equal to, if you took the first derivative of r of t first, if you took the first derivative, there we go, if you took the derivative first and then multiplied it by c. So basically the c can move anywhere. It could stay inside before you differentiate, or it can be outside, and then you can add it in or consider that after you differentiate. Okay, so that's the first one. Number 2 is the product rule. So product rule, and there are a couple different product rules. This is the first one that we'll see. So product rule says for, here I'll make the colon more noticeable there. So for any differentiable, scalar valued function, scalar value. So this is the kind that we're used to, scalar valued function. And we'll call this f of t, So see how when it's scalar, that means it doesn't have a little arrow on top like the r's do, right? Okay, and a vector valued function, here we go, r arrow of t, right? So that's a good comparison there. Okay, then that means that the derivative, ddt, of f of t times r of t, so for multiplying these two functions together, the derivative comes out as the normal product rule, but now we just have, so first times derivative of the second, okay, so that would be f of t times r prime of t plus derivative of the first, so f prime of t times the original, the second, okay, so r of t, r arrow of t. Okay, so that's the first product rule that we see. And now we'll move on to the chain rule. Okay, so we're still on rules for differentiation. This is going to be the chain rule. Okay, so in this one, it says for any differentiable, so differentiable, and again, we're going to have a scalar valued function, and we'll call this one g of t, just to mix it up here. Okay, then we have the d dt, so the derivative of, with respect to t, of r of g of t, and then the inside one is a scalar valued function, not another vector one. Then we're going to have, basically you differentiate the outside, so the derivative of the outside by keeping the inside function the same, and then we're going to multiply that times the derivative of the inside, so d dt of g of t, which turns out more nicely to look like r prime of g of t. So we're going to keep the inside the same, and then have the first derivative of the inside at the end there, tacked on to the end. Okay, so this is like the chain rule basically. Now we're just dealing with vector valued functions along with scalar valued functions. Okay, so now we'll move on to, here's another product rule, but this time we have the product rule for, wait for it, rule for dot and cross products. Because these involve vectors now, so we're going to get a little bit more complicated, but not really. So for the dot one, here I'll draw a line there and make it look nice. And then so for the dot product, an example would be ddt. So we're going to take the first derivative of vector valued function called p arrow of t times q arrow of t. Okay, so this is going to be equal to, we're basically going to do the same thing as the normal product rule, but just the multiplication is going to be the dot product instead. So we're going to have a p of t multiplied, and this time this means dotted with q prime of t. Okay, so that's our first grouping there. And then we're going to add that to p prime of t dotted with q of t. Okay, So it's basically, it follows the essential form of the product rule for differentiation, but instead our multiplication is not just multiplying like normal, like with constants or scalars or anything like that, but this is going to be with vectors, so that means the dot product, if you're taking the derivative of two things dotted with each other. Okay, so that's the dot product one, and now for the cross product, it's basically going to be the same. So here's the cross product one. We have ddt of, we'll use p and q again, so p of t crossed with q of t. Okay, so this is going to equal, again, we're going to have the same thing, so same format here, but now our multiplication is going to be the cross product. Okay, so there's our first grouping, and then we have that the same thing replicated here, just flipped around. Again, the cross product in the middle there, that's our multiplication function, or our operation that we're going to do. Okay, so that basically lays out the product rule for our dot and cross products. Okay, so now we're going to enter the zone of tangent vectors. So we're going to use the derivative and relate that to the tangent vector. Instead of the tangent line, now we have tangent vectors because we're dealing with vector-valued functions. Okay, so basically, r prime of t naught, so the derivative of the vector-valued function at a certain point, this is what it does. It points in the direction tangent to the path, so tangent to the path, r of t, path of, there we go, of r of t at t equals t naught, okay? So this is what it's saying. Basically, this is where it comes from, is let's say you have some function, okay, and it goes like this for some reason. And so here's like r of t naught, okay? So this is the point r of t naught, all right? And let's say you have another point over here called r of t naught plus h, okay? So we added an h in for the t value. So as you move along, here's where you are later on in the curve, okay? So if you were to take a line from here to here, kind of like a secant line, remember those? Then you would get r of t naught plus h minus r of t naught over h, okay? But then basically as you move this line, this h, as h goes to 0, so as it gets closer and closer and closer and closer, then we're going to start looking more or less like this. And you guys can probably guess what it's going to look like. But so we're going to have our r of t naught, right? So that's there. That's our vector there. As we get closer and closer, let's say we're here now. Okay, this point, that was a really bad arrow. I'm sorry. But okay, so here's our r of t naught plus h. And I'll draw another one here. So we're basically going to go until we are really close to that point there. So at this point, as h goes to 0, then we're going to have something that looks like that, which is tangent to the path or the curve or whatever you want to call it. To the path, we'll say path, because we're talking about r of t. And this arrow here, this is going to be represented by r prime of t naught. This is our derivative, okay? So this is the way we're going to parameterize a line. So I'll continue on the next slide. So we have, I'll draw this last picture here. So we have that, this is r of t, okay? This was r of t naught. Okay, and we have a vector coming from, based at the origin. And then here's our tangent vector sticking out like that. So this is r prime of t naught. So this is how we're going to parameterize the tangent line. So tangent line parameterization. And I'll abbreviate, parameterization, okay? So this, the way we're going to parameterize this is, first of all, this tells us our slope. The r prime of t naught is our slope. So slope is given by r prime of t naught. This is like our, remember when we were learning before, this is like our v, our direction vector for our line, right? When we're parameterizing lines. So here's our line, and r prime of t naught tells us the direction in which we go, okay? And so this is, if this is like our v, then our, I'll actually name it something a little bit different. So this will be L of t. This is our line, okay? So L of t is the name of our line. This is going to be r prime of t naught, and it'll consist of all scalar multiples of that direction vector. So we have to have a t in front as our variable. Okay, but this line, as you see, it does not go through the origin, right? And it doesn't necessarily have to. So what we actually did was translate this line with the same slope. We translated it up to here via this vector, okay? And that vector we can call r of t naught, right? That's how far we traveled. So r of t naught. That's how much the line was displaced or moved, okay? That's how much it was translated, so to speak. Okay, so this is going to be our the parameterization for our tangent line. All right, at t naught, that is. Okay, so another thing to note is that when r of t has constant length, so this is a different topic, okay? So when it has constant length, that means that r of t is orthogonal, so that means perpendicular, right? Orthogonal to r prime of t, okay? So here's an example of this. Let's say r of t has constant length. So what does that mean? That basically means a circle, which this circle is probably not as circular as you can get, but there we go, that improved it a little bit. So r of t means that like any point that you are on the path, that's the same distance away, okay? So that would be a circle, or even in 3 dimensions, that could be a sphere, right? So if we have a sphere, that would be the same concept there. We have the same length of our vector. Okay, so here's a sphere, and you'd have the same length of your vector all the way around. Okay, so circle and sphere, primarily, those are the only 2 examples I can think of, really. So what this means, though, and I'll explain why this is. So if r of t has a constant length, that means the magnitude of r of t is a constant, right? So it's going to stay constant, it doesn't change. So that when you take the derivative of the magnitude of r of t, then that means that, so derivative of magnitude of r of t is going to be like the derivative of a constant, okay? And that we all know equals 0, okay? And it would be the same exact thing if you were to square it, too. So derivative of magnitude of r of t squared is equal to the derivative of c squared, which still equals 0, okay? And I'll continue this on the next slide explaining why this statement is true. Okay, so if we know that d dt of the magnitude of r of t squared equals 0, then we can kind of work with this side, okay? So remember how magnitude of something squared is equal to the dot product of a vector with itself, okay? So this is actually this, all right? Remember, we learned that before in an earlier video, I believe. So basically, I can rewrite it like this. This is equal to this, the arrows that I'm drawing, right? These are equal. And from here, we can apply the product rule for the dot product that we just learned. So let's do so. So we have d dt of, okay, hold on. I didn't need to write that again. Just kidding. Okay, so we have d dt of r of t dotted with r of t. So the first one's going to stay the same. And we're going to dot that with the derivative of the second one, which is r prime of t. Okay, so that's our first grouping. And then we have that added to the derivative of the first one, so r prime of t, dotted with the second original function there, the original vector valued function. So these are actually the same, right, because we were just using r of t's for both of them. So this is equal to 2 times r of t dotted with r prime of t, okay? And now you might be like, okay, so this tells us what? And if you'll recall, this is equal to this, which is equal to this. I'll just keep boxing things, which is equal to 0. There we go. So the key point to remember here is that this thing that we ended up with is equal to 0. And if you divide by 2, that doesn't really do anything to the 0. So that means that r of t dotted with r prime of t equals 0, which, if you'll recall, if you get the dot product, if you end up with a dot product between two vectors equaling 0, that means that those two vectors involved are orthogonal to each other. So we're going to say, therefore, R of t must be, that rhymes, perpendicular or orthogonal to R prime of t. Okay, so big conclusion there. All right, so they must be orthogonal.